Right, now that we've got our linear system of equations represented as an augmented matrix, in order for us to solve the system of equations using matrices, we'll have to establish what are referred to as the row operations, or sometimes elementary row operations. And we see here the three things that we get to do without affecting the solution to the system of equations. So we can interchange two rows. We can multiply a row by a non-zero scalar, which is really just a fancy word for constant. And we can replace a row with the sum of a multiple of another row and that row. This one's a little bit more confusing, and we'll do all of these as examples just to make sure we understand what's happening here. But these are essentially extensions from what we already know about solving systems of equations, and we can understand them by remembering that each one of these rows represents a linear equation. It should be apparent, at least in the case of 1 and 2, these processes do not affect the solution to the system in any way. In other words, it doesn't really matter if I write one equation first or a different equation first or second. The solution to the system is unchanged or remains the same. So let's work through an example and see how we can apply these particular row operations. So let's start by just swapping a couple rows. So just as an example, I'll go ahead and swap row 1 and row 3. And here's some notation we can use. So this is going to indicate that we want to interchange row 1 and row 3. So row 1 now becomes 2, 4, negative 2, 2. The second row is unchanged. And the third row is 0, 2, 1, negative 2. So simply swapping rows. Let's do an example of the second rule, which is to multiply by a non-zero constant. So we'll multiply the top row by 1/2, which is really the same as dividing all elements by 2. But in the context of what we're doing, we typically refer to this then as multiplication by a scalar. And so we'll just cut each of them in half. So 1, 2, negative 1, 1, and everything else will remain the same. So there you have multiplication by a scalar. So now let's practice this rule where we can replace a row with a combination of other things. So in this case, we'll make a new row 2, and I'll just indicate that with a little star here. And this is going to be equal to minus 3 times row 1 plus row 2. And this will be, again, our new second row. Everything else in the matrix will remain the same, so we can rewrite all of that. So 1, 2, minus 1, 1. The first row isn't changing, and the third row is also not changing. But again, we're going to get a new second row, and we'll do this by multiplying the top row by negative 3 and adding it to the second row. And that, again, will create a new second row. And we can do this by writing it all out, or we can just do element by element, and that's usually how we do it. So minus 3 times 1 is minus 3, plus 3 is 0. So we get a 0 as the first element in the second row, and we just repeat that process. So minus 3 times 2 is minus 6, plus 5 is negative 1. So the second element here is negative 1. And again, negative 3 times negative 1 is positive 3, plus negative 5 is negative 2. And lastly, negative 3 times negative 1 is negative 3, plus the 1 is negative 2. So that now becomes our new second row. Again, we could, if we needed to make sure we get it right, multiply the top row, -3, -6, 3, -3, and then put the second row below it, 3, 5, -5, 1, and then we could add them together to get 0, -1, -2, -2. Again, we get the same numbers for that second row. We just don't always do it that way. It's a lot of excess writing, and I think we can do the arithmetic in our head. But if you feel like writing that out helps you get it right, then by all means, I think you should probably write it out. Okay, so now we've practiced all three of them, and we're actually working towards a specific goal here. And I'm just going to go ahead and finish out just so we can get a little bit more practice with this row operation stuff. So the next thing I'll do is I'll multiply row 2 by -1. This is -1 times row 2. And we'll get everything else staying the same. Row 1 will remain unchanged. Row 2 is going to be 0, 1, 2, 2. And row 3 is unchanged. So that's our new matrix. And let's make a new row 3 now. So we'll get to practice that rule again. So our new row 3, again, I'll use an asterisk to indicate that this is a new row 3, is going to be -2 times row 2 plus row 3. And again, row 1 is unchanged. Row 2 is unchanged. And now we'll get a new row 3. So I'm going to multiply row 2 by -2 and add it to row 3. This is generally an easier way to do it than trying to do some subtraction or something like that. So here we go. -2 times 0 is 0, plus 0 is still 0. -2 times 1 is -2, plus 2 is 0. -2 times 2 is 1, is -3. And last, -2 times 2 is -4. -2 is -6. Again, if you need to multiply that up separately and then add the two rows together, that's fine if you feel like that's what you need to do. So now we've got, again, one more equivalent matrix. And I'm going to do one more step on this, and that is I'm going to go ahead and multiply row 3 by -1/3. And make one more equivalent matrix. Again, everything remains the same except for that third row. 0, 0, and we get 1, and then 2. So here, multiplying by -1/3 is doing the equivalent of dividing -3 and -6 by -3 to simplify that particular equation. Remember, each one of these rows is really representative of an equation still. And at this point, if we wanted to convert this back, we could rewrite this as a system of equations, remembering what each one of these columns represents. These are the coefficients on x1, these are the coefficients on x2, these are coefficients on x3, and the bar is your equals sign, and the constants there being on the right. So I could rewrite this now as x1 plus 2x2 minus x3 equals 1. And we have a 0 coefficient on x1, so we don't write it down. And I get x2 plus 2x3 equals 2. And then in our third equation, or third row, I have x3 being equal to 2. So the row operations that we went through, what makes them special, again, just as a reminder, is that they create equivalent matrices. So that means that the solution is unchanged when we perform those operations if we've done it correctly. So now I have a much simpler version of my system of equations that we started with. You'll remember this is what we started with. Way back up here, here is our example that we started with. And from that perspective, there's no way we would be able to read off the solutions. But now that we've got through some of those row operations, we can actually pick off what the x3 solution is and then back solve pretty quickly to figure out what x1 and x2 are. We could continue on this process even further, and this is something that we'll explore in the next lesson, which is referred to as Gauss-Jordan elimination. And the goal there will be to completely solve it out to a specific form known as reduced echelon form, and that will generally be our goal. Now we can do that on our calculators, and I'll try and show you how to do that in the next lesson, and that'll get it to us a lot quicker, or we can even use Octave Online to help us compute some of these. There's other online linear algebra calculators that can be helpful for row reducing particular matrices. As it turns out, it's still really important that we understand how to use these row operations. They will be applied in cases down the road where we won't be able to do them in a calculator or some sort of other computer algebra system. So we will still need to know how to solve these things by hand. So it's important that we take the time to learn the row operations now.